We're going to go over a couple methods to create external threads. So I'm in my personal shop because the IME labs are closed during this coronavirus pandemic. So I'm in my personal shop. I'm going to show you a couple methods of creating external threads, and we'll get started right now. The first method we're going to use is with a threading die. And so this is the die tool. So you can see there are threads inside. Those are hardened steel so that they cut material rather than the cutting edge being removed by the material that you're cutting. This happens to be a half 13 thread. I don't know if you can see that on the camera. Half is the nominal outside dimension, and then the 13 is the threads per inch. So this is the portion that does the actual cutting, and then we have this handle which we use to hold the die. So we put the die in the handle, tighten it in there, and then we are ready to cut external threads. So I have prepared a blank. So a blank is a piece of material that has a portion of the machining complete, and that blank is what we are going to thread. So this is set up to do a 1/2 inch 13 thread. So the outside diameter of this is about 0.495. To figure out what size diameter you need before you thread it, we have a chart in the lab manual that you would look up. You would look up the thread size that you want to create, and then it would give you the major diameter of that thread with a tolerance range on it. So I have already created that blank, and then it's time to start cutting threads. So in this case, I'm just using the lathe as a convenient fixture to hold the part. So I'm not going to actually turn the machine on during this operation. It's just a good way to keep the threading die lined up with the part. So whenever you're cutting threads, both internal or external, we need to apply some cutting fluid, and that acts as a lubricant. And then I'm going to place the die on the part, and then I'm going to slide the tailstock in so that it actually touches the die handle a little bit. That gets everything nice and square. And then, as I mentioned, I'm not going to apply power. I'm just going to rotate by hand. So I'm pushing with the tailstock, and you can see some chips starting to fly off there. Once I get the die started, I can back the tailstock out of the way. I can move the carriage out of the way, and then now I'm just going to be doing the threading by hand. So I'm going to rotate about a turn, and then I'm going to back it up. That breaks the chips that I'm cutting, and I'm just going to keep doing that until the thread length is correct. In this case, on this example, I'm just going to go until I get to the shoulder. There we've got the die up against the shoulder, so we can back the die up a little bit, pull the handle off, and then we can back the cutting die off of our part. You can see the threads are nicely cut there, and to double check, we can put a hex nut on there. So this is just a standard hex nut, and the hex nut goes all the way on. You'll see that is about where it stops because there's a lead-in portion to the die. So if you look at the die, the threads are not fully formed all the way in, all the way to the edge. So there is a taper so that all of the cutting is kind of equalized over the first few threads. So if you need a nut or the internal thread to go all the way to the shoulder, you would add in a thread relief. So I'm going to add a thread relief, and you can see what I mean by the nut going all the way to the shoulder rather than stopping a little bit short. So you can see that the trailing end of the threads is gone, and now this nut will thread all the way up to the shoulder. So if the camera angle didn't show it before, the nut would only go about that far. Also, the thread relief is convenient for other threading methods. In fact, the next method that I'm going to show you is called single point threading, and the thread relief feature is required for that, and I'll explain why here in just a minute. And the machine needs to be set up. So this is the feed rate and threading chart, and so we need to pick the appropriate setup for the threads that we're creating. So we're going to single point thread a 1/2 13 just like we used for the die, And the only thing that the machine cares about is the 13 threads per inch. The ½ inch, the machine doesn't care what diameter we're doing. It just needs to feed at the appropriate rate. So these larger numbers are the threads per inch. The smaller numbers are the feed in inches per revolution of the chuck. So for threading, we want to set it in threads per inch, and so we want to be right here at this 13. So to get 13 threads per inch, we need to be lined up with the 8 column, and so the 8 corresponds to this dial, so I've set that. And then the 13 also corresponds to A and E. So if we look over here, we've got a lever that I've set to A and then another lever that I have set to E. So the machine should be all set to go. We've got the blank prepared for the single point threading operation. So you can see the thread relief is already cut in there, and then we've got the major diameter already machined. This is the threading tool, so if you look closely at the threading tool, we have an included angle here of 60 degrees. This specific threading tool is called an indexable threading tool, so it has 3 different cutting edges. So when this cutting edge gets dull, then we loosen this screw in the center, rotate it around, and then we've got another cutting edge here and another cutting edge here. So as far as the blank and the tool, we're set to go. Before we start cutting, I wanted to point out the reason for the thread relief when single point threading. That is, we need an ending zone for the cutting edge here. And so we are going to be feeding along, and the timing of the feed to the rotation of the chuck is very precise. And so we need to stop at exactly the same point every time. If we're feeding along in a workpiece and we stop, say, in the middle, then we lose our thread, so it just creates a groove. If we continue to feed and we crash the tool into this shoulder, obviously that causes other issues like ruining the part and the tool. So we need to consistently stop the cutting edge in the same place that won't ruin the thread and won't ruin the part. So that ending zone is this thread relief. So that is the convenience of the thread relief when single point threading on a lathe. We're going to make our first cut now. So I have dialed the tool in so that it takes about 20 thousandths off of the diameter, and then I'm going to stop precisely at that thread relief. So that's going to look a little bit like this. I need to wait for my thread chasing dial. There we go. And you can see that coming off, and then I need to stop right there in that thread relief. When I was talking about the thread chasing dial that I was referring to, it is this dial that's slowly rotating, and so that is showing the relative position of the lead screw, which feeds the carriage, to the rotation of the chuck. So I need to engage my feed at the same place every time, and so that's what those numbers that are slowly going past are representing. So the thread chasing dial is right here. This is the lever that engages the carriage to do the threading. So I wait for a specific number on the thread chasing dial, and then I engage. And about 10 passes later, we have the completed single point thread. So you can see both sides of the part have the 2 different threads that we've created today. So the die on the left side, and then the single point threaded threads on the right side. So both look similar, they function similar, and so you're probably wondering why there are 2 different methods. The 2 threading methods are both very commonly used that we talked about today. The one with the die is obviously very fast, and it takes a specific tool to make each thread. So if you don't have a specific tool to do the thread that you need to do, then the single point threading method is used. So again, single point threading can do any combination of diameter with number of threads per inch that the machine is capable of. So again, the machine has a range of threads per inch that it is capable of doing, and then the diameter is just a limitation of the machine. So if you wanted to do custom threads that don't necessarily match an industry standard, you can do that with single point threading, where with the die method, you need to have a die for each individual thread size that you're creating. Again, the advantage of the die is it creates threads significantly faster than the single point threading method. Now that we've completed external threads, we're going to work on internal threads. So for the purposes of this class, any internal thread that we create needs to have a hole that we put those threads into. There are some hybrid manufacturing processes used in industry that create the hole and the thread at the same time. But for this class, we're just going to say that we need to create a hole before creating an internal thread. So the tool that creates an internal thread is called a tap. So the tap is pretty much the opposite of a die. So this is the tap. You can see the threads are on the outside of it. And this tap happens to be a 1 inch and 1 1/8 by 12. So that's 1 1/8 outside diameter and 12 threads per inch. So in order to figure out what size hole to drill, we have a thread chart, tap drill thread chart. So your IME lab manual also has a copy of this. The way it's arranged is in 3 individual columns, and there are a number of those columns. So the first one says the fractional or drill size. And so drills come in fractional sizes. When I'm talking about drills, I'm talking about inch size drills. So they come in fractions, numbers, as you can see, and letters. And so we have the size of the drill here, we have the decimal equivalent, and then if there's a tap associated with that hole size, then the tap size is also listed. So if we needed to determine what size drill to use to create a hole, if we were going to do this 1 1/8 12 threads per inch hole, we look at the chart, we find the thread size that we want, and then we move over and we see it's a 1.046, or that is 1 3/64. So that would be the drill size that we use before we create that internal thread. So I'm going to show you how to manufacture internal threads. For all of our examples, we're going to use 1/4 so that's 1/4 inch outside diameter, major diameter, and then 20 threads per inch. So from this chart, I see that we need to use a number 7 drill, which is a decimal equivalent of 0.201. So I've got a blank prepared with 4 number 7 holes drilled. So those again correspond to the tap size that we're going to be using. And again, you get that from the chart, either on the Google in the lab manual, or a lot of times machine shops will have a chart on the wall. So this is the 1/4 tap that we're going to be using throughout the various machines and examples of how we're going to thread. And so this first method is just by hand. So I have this tap wrench, and the tap wrench works very similar to the way we were holding the die. It grabs the tool. In this case, we have square jaws inside to grab just the square portion of the tap. And so we're going to tighten it down. Now that tap is in there. Anytime you're cutting threads, either internal or external, you need to apply some cutting fluid. And then this first method, again, I'm just going to do it by hand. So you kind of have to eyeball that the tap is coaxially aligned to the hole. So once it's all squared up, then you just start rotating the tap, and it takes a while to get onto it so that it's square. But after some practice, you can usually get it okay, not as good as if it were a machine. Once we get it started, you can see it's stable, it stays there by itself. Then we're going to back it up about every turn. So again, we're producing a chip that is cutting the material out. That chip needs to be broken so that it doesn't get all bound up and cause problems. So I go down and then I back it up, and I just keep doing that until I can tell that the torque is significantly less, and that means that the threaded hole is all the way through the part. In this case, I have a plate, an aluminum plate that is 0.25 thick. So you can see some of the metal chips that are left on the tap. And then if we look close right here, you can see the threads in the part. The next method of creating internal threads that I'm going to show you is one step better than just threading by hand. It's using a cordless drill, so the tap can go directly in the drill chuck. And then we're going to apply some cutting fluid again. And then we're just going to square it up to the part as best we can. And then we can just drive the tap all the way through. So with a spiral point tap, as this one is, we can just continue to go through without breaking the chip. It usually makes a better thread if we do back it up and break the chip, as I showed the first time, but it does work to just go all the way through. And so if you look closely, you can see the threads that we just created right there. Again, this is one step better than just by hand because you don't have to turn it, but it doesn't get the threads as square to the hole as a lot of applications require. This method of creating internal threads is by using a drill press. So the drill press holds the tap nice and square in the drill chuck. And so this is the best method to get it squared up on a manual machine. The disadvantage of this method is a lot of drill presses only have a forward direction. So when you reach the bottom of your tapped hole, you need to shut the drill press off, remove the tap, and then back it out by hand. So I'll show you what that looks like. Again, we need to add tapping fluid or cutting fluid to the tap for lubrication. And then we're just going to slowly feed the tap through. And then as we get to the bottom, now I'm going to release the tap. And at this point, I will put on the tap handle to get the tap out of the part. So again, this is a little bit time consuming, but it does yield a very good thread because the drill press holds the tap nice and square to the part. One more way to create internal threads on a drill press is with a tapping head. And so this tapping head is self-reversing. So as we turn the drill press on, it rotates the tap in the correct direction. As we get down near the bottom, there's a clutching mechanism inside. So as we stop forcing the tool down, so once we stop doing that, the clutch engages and the drill press is still spinning, but the tap is no longer spinning. If we then reverse the direction of the feed, so that is we pull up on the drill press, then that actually reverses the tap and we can get it out of there. So this is about the fastest way to manually thread an internal hole. So I'll show you that real quick. Again, tapping fluid is our friend whenever we're cutting threads. So we'll put some of that on. So you can see I'm feeding down. I stopped feeding, and then now I'm going to pull back up, and the tap is reversing. The last method of creating internal threads that I'm going to show you is on a CNC machine, computer numerical control. And that happens to be my personal favorite because it's completely automated. So once it's programmed, once everything's set up, you push the start button and all of the tapping is done automatically. So the process is called rigid tapping when it's on a CNC machine. And so rigid tapping means that it times the rotation of the tap with the feed. So very similar to on the lathe when we single point threaded. So the two were timed together. It's electronically timed together on a CNC machine. Otherwise, you would either break the tap or pull the part out of your work holding device. So typically on an enclosed CNC machine like this, you would have flood coolant. In this case, I'm going to leave the flood coolant shut off so that you can actually see the tapping process. Flood coolant makes such a mess that you don't actually see the machining process a lot of times. So I'm going to leave that shut off so that you can see the process a little bit better, and I'm going to apply tapping fluid just manually like I have on the other operations that I've shown you. Once the program is loaded in the CNC machine, the part is loaded in the work holding device, and the tool is loaded in the tool carousel, we're ready to machine our part. So I just need to hit cycle start. The machine is going to pick up the tap from the tool carousel, and then it's going to turn on the spindle. And that is all there is to it, to the rigid tapping. Once we're done threading all the holes, we can grab a socket head cap screw. This happens to be a 1/4 20, which corresponds to the threaded holes that we created. And our socket head cap screw threads right in.